sorry, I just handled the camera. So we only observe a part of that. So why have we introduced something that is complex? That means it has an imaginary part, and something which is imaginary does not exist. And it needs us in complex manipulations, complex calculations. It's difficult to understand at the beginning. So what is the advantage of that? Well, the advantage is apparent at the time you decide to make time derivative or integration against time. Because you have the exponential function here. So what is the derivative of an exponential function? Well, it's very simple. A derivative of e raised to anything times t against t is that anything times the original e raised to anything times t. So the important point is that if we have a phasor that has the j omega t time dependence in it, the derivative of that phasor is j omega times that phasor. So I will put it down. So if we have a time derivative of a phasor A is j omega the original phasor A. If we had to integrate it against time, we would have the original phasor divided by j omega. So this is the main advantage. We can easily carry out time derivatives within this phasor space. Now this has been so simple and so nice that we as electrical engineers have for years only investigated time harmonic signals. Because it's so simple, so we have mostly forgotten about the fact that the reality is in time domain, and we have been using only time harmonic dependence of the signals, sine or cosine, because it's so easy. How easy? Well, I will rewrite the equation now using phasor for the electric field strength. Now that would give rise to something very strange. There will be something like a vector. So, and we will have an arrow over the, and there will be a head over the arrow. It will be a phasor of a vector. But it will give us the possibility to forget about all time derivatives. So on cost of introducing phasors into the equation, we will have one less variable. Time would not appear in this equation for E phasor. I will put it down. So just Laplace on E would not change, we will just have the head on that. Now here we could replace the second derivative of E against time by j omega times E phasor, and here we would replace this just by mu sigma, and the derivative would be replaced by simply multiplying j omega. Okay, let us do it. What we had there, we had minus mu epsilon. Now there was the second time derivative of E against time, so that is multiplying by j omega and by j omega again, so I will do that. And we have to handle the other time derivative, minus mu sigma j omega E vector phasor makes 0. And now we have only to get those j omegas into some more fashionable way. So here we have j times j, which is minus 1. So our equation gets to plus mu epsilon omega squared E vector phasor minus mu sigma j omega E is 0. Well, this is quite nice, but there is a better notation of that if we just rearrange the terms. So we could have it like Laplace applied on E plus k squared E makes 0. With a short remark that tells that k is equivalent, k squared is equivalent to minus j omega mu times j omega epsilon plus sigma. Well, so this is a formulation of the wave equation that is valid for time harmonic signals, and it seems to be quite simple, noting that we have to obtain the wave number k or its square in this manner. Now, having this equation, we should do some short discussion. We have somehow get rid of time in our equation. Still, we have 3 space coordinates, x, y, and z. So we still do have a partial differential equation. But now we possibly can have a work about it, a work about those many coordinates. What if we know the direction of propagation of the wave? In that case, we can turn our coordinates so that, for example, the z coordinate points to the direction of propagation. Well, if the wave propagates only in one direction, it means that in the other directions it will be constant. And if this is true, the time derivatives against y and x, sorry, the space derivatives against y and x would be 0. And the second derivatives against x and y, that is derivatives of 0, would be 0 again. And therefore, if we turn our coordinate system so that the z-axis points to the direction of propagation, we would have only one variable, z. And our equation that originally was partial differential with 4 unknowns now gets into an ordinary differential equation with derivatives only against z. Let's do that. It seems that we finally obtained something that could be understood. So we have an equation telling that the second derivative of the phasor of electric field strength against x plus k squared e vector phasor makes 0. And as such, this is a simple equation. To classify it correctly, it is a differential, an ordinary differential equation of the second order with constant coefficient k. And such an equation has a simple solution that can be written in a simple fashion. I will show you the equation that governs the solution. It is E, and we know it's a vector and phasor, as a function of the variable z is given by, now it is a differential equation of the second order, and we will have at least two functions that will describe it. So that will be some constant c1 multiplied by an exponential e minus j k z plus c2 multiplied by an exponential e raised to j k z. Now we have this solution, and it is still rather complex to be understood. Why? Well, from the mathematical point of view, we had the differential equation, which was ordinary with constant coefficients of the second order. It has this solution. What it means from the way of physical insight? Well, we have made the assumption that the wave propagates along the axis of z. Well, but there are two ways of propagation along the z-axis. One is from minus infinity z to plus infinity z. The other is from plus infinity z backwards to minus infinity z. All those two cases propagate along the xz, one in the positive direction, one in the negative direction. So we need two waves, one going forward and one going backward. Now we have to distinguish which is which. To do that, possibly Well, is there any way, any thinkable way, to watch again the first TV transmission or the first broadcasting as to Europe? The first broadcast from Europe was a British broadcasting. The second European broadcasting was from Prague, so that was the first on the continent. By the way, it was at 30 kilohertz, and it was quite, the technology was quite funny from today's view. But anyway, that broadcasting was on long waves, and that means that it penetrated the atmosphere and ran into space. Well, it was some 100 years ago. So is there any thinkable way how to get it again? At that time there were no tape recorders, no MP3s, so there was no record of that broadcast. It has been sent into space. Some people could receive it with their radio receivers, and it's out there. But if you, for example, asked Captain Kirk with his Enterprise, he could easily do that, because he would jump on the starship. As you remember, Enterprise was not limited by any speed of light. It has the warp acceleration 5.3. So he would just jump into Enterprise and move 100 years from the Earth and just turn his antenna back to the Earth and wait for the signal. And suddenly there would be the signal of the first broadcasting in the world, then the first broadcast from Britain, then the first broadcast from Prague. But what does that mean for our equation? Well, it means that if you move along the direction of propagation, and I mean if you freeze the wave and move along the wave with a velocity greater than light, then you would get into the history of the wave. So, bearing that in mind, we know that the minus exponential must be the wave propagating in plus z direction. So, the argument decreases as we move along the z direction. So, for the sake of simplicity, we will from now only treat the wave that is propagating in the z direction, and therefore we will neglect this second part of the solution. We have a simple equation for the wave that propagates in the direction of z. Now, we have on the left side something which has the dimension of electric field strength. We have here the exponential, and as you know, the exponential function is dimensionless. And therefore, this constant c must be physically electric field strength somewhere. Where? Well, we will find, let's put z to 0. Then this exponential gets to unity. So this constant must be the phasor of the propagating wave at z equivalent to 0. And we can then call this constant E0. So we have a new form of the solution which says that Ez vector phasor is the phasor of the wave at the beginning of coordinates times e raised to minus j k z. Now I will shortly think about the k. K is the wave number. We still do not know how k looks like, but it is known by its square. The square of k is here. Now let us consider k like a complex number which has a real part and an imaginary part. So let's set up k that would be equivalent to some beta minus j alpha. Beta minus j alpha. And let's look what happens with the equation now. So, bearing in mind that k has the form of beta minus j alpha, we would get another form of the solution, which I would write directly here. So again, we have the electric field phasor at the beginning of coordinates, that is for z equivalent to 0. Let's call it E0. And then we have to multiply it by two terms to obtain the electric field strength phasor at any other coordinate. And those two terms would be E raised to minus j beta z and E raised to minus alpha z, where beta is the real part of the propagation constant and alpha is the imaginary part of the propagation constant. Now, having this in mind, we can a little bit understand the physical meaning of those two parts of the propagation constant, that is the real one and the imaginary one. Look, if you evaluate this expression, you have here the phasor at the beginning, but now we have two parts. This is Euler's number raised to a purely imaginary exponent. Now this always in magnitude is 1. It has different composition of real and imaginary part. You can see different argument. But as to magnitude, it lays on a unity circle. So this part of the equation only governs the argument of the phasor that results out of it. It changes the argument, but there is no change in magnitude. Now, this part of the equation is an exponential raised to a real number. This part of the equation always has a zero argument. It does not change the argument of the result, but it decays with distance based on the fact that alpha is non-negative. It decays with distance. So this part of the equation gives you the damping of the wave. So we have decomposed the solution into two parts, two functions. One of them governs the change of the phase of the propagating wave along its trajectory, and the other part depicts the decrease of the magnitude of the wave along its trajectory, which is called damping or attenuation. Your questions, please. Well, as there are no questions and as we have done a big part of work, I will again make a 5 minutes break. Then we will still have the same paper with formulas. I will ask you 4 questions again, and only after replying any eventual questions, I would go on with further attention paid to the propagation constant k, because that's a piece of important job of today. So see you in 5 minutes.